We're still looking at Chemistry 1123, page N. This time there's 2 problems to solve. I just want to help you if you're stuck on it to get it set up, and I'll let you finish it, okay? We need to notice on problem 72 that we're going to use this formula. It tells us the total atmospheric pressure to be 750, and then it says that a gas is collected over water vapor. Now, as you read the PACE, you noticed that it said the total gases in a container will be equal to, will add up to the atmospheric pressure. So if you have 2 gases, let's say oxygen and carbon dioxide in there, part of it will be carbon dioxide, part will be oxygen, and part will actually be water vapor, okay? And that's because gases are usually collected over water, and the PACE kind of explains how they do that. If you're interested to learn more, you might just do a quick check on YouTube videos and see if you can find a video that shows that happening. But the amount of pressure from the water vapor has a lot to do with temperature. So the lower the temperature, the less water vapor is dissolved in that sample of gas air, okay? At higher temperatures, we'll have more water vapor and therefore less of the gas that we're trying to collect. So this particular problem tells us that this is happening at 25 degrees. So I'm looking here at the table, 3.7 on page 20, and it says at 25 degrees, the pressure of water vapor is 23.8, okay? And that is torr, okay? So that's important to always check. Make sure we're talking about the same units. If this had said 1 atmosphere, I would need to convert this to 750 torr. All right, and I don't need to finish. You can do the math, okay? Well, how would you find out what this missing number is? Do not add these 2 together, okay? This is going to be a smaller number, so that when you add these 2 together, it equals 750, okay? I'll let you finish that one. And now let's talk about problem 73. It says a chemical reaction produced 980 milliliters of nitrogen gas, N2, at standard temperature and pressure. So the reason they're telling us that standard temperature and pressure is because there is a fact, and the PACE talks about this, that if you have 1 liter of gas, it will contain 22.4 moles. Is that correct? Let me just double check my memory here. No, 1 mole is 22.4 liters. I had that backwards, okay? So we're going to start with what they give us here, which is 980 milliliters. Put that over a pedestal, and we're going to convert this, first of all, to liters. So we're going to go from milliliters to liters. 1 liter is 1,000 milliliters, okay? So that unit will cancel, and now we're going to go from liters to moles. 22.4 liters of any gas will have 1 mole of that gas, all right? So if I just solve this much of it, let me get my calculator. Let's see what we get. So we multiply this, this cancels this cancels this. So the answer comes out in moles. So 980 divided by, we're going to multiply this times 1,000, so 22,400. So we get 0.04375 moles. Now, the next thing we have to figure out, because the question it asks is how many grams, how much mass of gas is in that many moles. So now it's important to look at the identity of the gas, because every gas, every element has a different number of grams per mole. So this is nitrogen. So I'm looking at the chart here, and it says that nitrogen is 14.0 0.0067 grams. He says, okay, Mr. Anger, I think I got this. I'll turn this off now because I'm just going to multiply the moles times the grams per mole. We'll have the answer. And you can try it. And then when you come back, we'll tell you why you have it wrong. The reason is, notice, and it tells us here in the directions, we are using nitrogen, but notice it calls it N2 gas. There are about 8 gases, oxygen, nitrogen, a few others, that you have to, anytime it's found in nature, it's always a diatomic, all right? So this is one of these diatomic molecules, so 1 mole will not just be 1 atom, it's going to be double this, okay? So we have to multiply that times 2. And I'm going to use my calculator because I want to carry it out to all those decimal places, and my Saturday morning brain doesn't feel like doing all this in my head. 0.0067 times 2, 28 something, and then, yeah, I guess I could have figured that out of my head. But anyways, we'll take that times the number of moles, okay? And then that will be the grams. Your final answer then, it looks like you were going to round off to 4 significant digits, all right? And how do we know that? In this problem, the 980.0 is the measured quantity, and so that has 4 significant digits, so our answer should have 4. We don't worry about temperature in these problems. This one doesn't have temperature, and in all of these conversions, that does not limit our answer, okay? That has infinite number of significant figures, and we just carry the math all the way through until we're done, and then round it off to 4.